Imagine a visitor from a distant star, a cosmic traveler carrying secrets from another corner of our galaxy. This isn't science fiction, it's the incredible reality of 3IATLAS, an interstellar comet that has journeyed light years to grace our solar system. Its fleeting presence offers us an unprecedented window into the universe beyond our sun, challenging our understanding and sparking our imagination. Get ready to embark on a thrilling journey of discovery. Our universe is vast and full of wonders, and every so often, it sends us a special delivery. 3IATLAS is one such package, a celestial messenger from beyond our solar system. Its arrival marks a pivotal moment in our quest to understand the cosmos. 3IATLAS holds a special place in astronomical history as only the third confirmed interstellar object to visit our solar system. Following the enigmatic 1I in 2017 and the more comet-like 2I Borisov in 2019, its 3I designation signifies this incredible rarity. Each discovery is like finding a message in a bottle from another star system, offering tantalizing clues about what lies beyond. These interstellar visitors are incredibly precious, providing direct samples of material from other stellar neighborhoods. They allow us to study objects that formed under different conditions than our own planets and comets. This direct observation is far more insightful than relying solely on distant telescopic views of exoplanetary systems. This cosmic wanderer was first spotted on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System (ATLAS) telescope. Located in Rio Hurtado, Chile, ATLAS is a robotic survey designed primarily to detect near-Earth objects that could pose a threat. Its unexpected discovery of an interstellar comet highlights the incredible versatility and importance of such astronomical surveys. The ATLAS system, with its wide-field telescopes, continuously scans the night sky, acting as humanity's vigilant sentinel. Its primary mission is planetary defense, but it also serves as a powerful tool for serendipitous discoveries like 3IATLAS. This underscores how scientific instruments often yield unexpected and profound insights beyond their initial design parameters. Like many celestial bodies, 3IATLAS carries a few different names. It's also known as C2025N1 Atlas, a more formal designation that tells us it's a comet, C, discovered in the second half of June 2025, N1, and by the ATLAS survey. Before its interstellar nature was fully confirmed, it might have had a provisional designation like A11PL3Z. These naming conventions, while sometimes seeming complex, are crucial for astronomers worldwide to uniquely identify and track celestial objects. They provide a standardized language for scientific communication, ensuring everyone knows exactly which cosmic body is being discussed. Each part of the name offers a piece of its discovery story. In the tradition of comet naming, these celestial bodies are generally named after their discoverer. In this case, the honor goes to the dedicated team behind the ATLAS survey. This practice acknowledges the hard work, technological prowess, and scientific dedication required to bring such distant objects into our view. It's a testament to human ingenuity and perseverance, recognizing the individuals and teams who push the boundaries of our knowledge. The name ATLAS now joins a long lineage of astronomers and observatories etched into the cosmic record through their discoveries. It's a small but significant way to celebrate scientific achievement. Understanding an object's orbit is like reading its cosmic passport, revealing its journey and destiny. 3IATLAS's orbital path tells a dramatic story of a visitor that is truly just passing through, a fleeting encounter with our solar system. Unlike the planets and comets native to our solar system, 3IATLAS follows an unbound, hyperbolic trajectory. This means its path is not an ellipse, which would eventually bring it back around the sun. Instead, it's on a one-way trip, using our sun's gravity for a brief slingshot maneuver before continuing its journey into interstellar space. It's a true cosmic nomad. This hyperbolic path is the definitive signature of an interstellar object. It tells us that the object's velocity is too high for our sun's gravity to capture it, confirming its origin from another star system. It's a fleeting encounter, a brief moment of shared cosmic space before it departs forever. The eccentricity of an orbit describes how much it deviates from a perfect circle. An eccentricity greater than 1 signifies a hyperbolic orbit, meaning the object will not return. 3IATLAS boasts a remarkably high eccentricity of 6.1396 plus or minus 0.0008, far exceeding that of its interstellar predecessors, ʻOumuamua and Borisov. This extreme value further solidifies its status as a true interstellar wanderer. This high eccentricity is a direct consequence of its immense speed relative to our Sun. It's not merely passing through, it's hurtling through. This characteristic provides crucial data for astronomers to model its trajectory and understand the forces that shaped its journey across the galaxy. At its closest approach to the Sun, known as perihelion, 3IATLAS will be moving at an astonishing maximum speed of 68 kilometers per second, 42 miles per second, relative to the Sun. Its hyperbolic excess velocity, the speed it retains after escaping the Sun's gravitational pull, is still a blistering 58 kilometers s, 36 miles s. This incredible velocity is a testament to the vast distances it has traveled and the gravitational kicks it received in its home star system. To put this into perspective, this speed is many times faster than any spacecraft we've ever launched. It highlights the dynamic nature of interstellar travel, where objects can be flung across immense cosmic distances at breathtaking speeds. This velocity also makes it challenging to observe for extended periods. 3IATLAS will reach its closest point to the Sun on October 29, 2025. At this moment, its perihelion distance will be 1.36 astronomical units, AU, which translates to 203 million kilometers, 126 million miles. This places it comfortably between the orbits of Earth and Mars, offering a prime viewing opportunity for our telescopes. Perihelion is often when comets become most active and brightest, as the Sun's heat vaporizes their icy surfaces. This close approach provides a critical window for scientists to gather detailed data on its composition and activity, maximizing the scientific return from this rare visitor. For those wondering about potential dangers, rest assured, 3IATLAS poses absolutely no threat to Earth. At its closest, it will not come nearer than $1.80, 270 million kilometers, or 170 million miles, to our planet. This distance is significantly greater than the distance between Earth and Mars, ensuring a safe, purely observational encounter. Planetary defense systems like ATLAS are designed to track such objects and confirm their trajectories, providing peace of mind. This safe distance allows us to study this interstellar guest without any concern for impact, focusing purely on the scientific marvel it represents. While not approaching Earth closely, 3IATLAS will make some interesting close passes with other planets. It will sweep past Mars at a distance of 19 cents on October 3, 2025, offering a unique perspective for any Mars orbiters. It will then pass Venus at 65 cents on November 3, 2025, and finally, make a relatively close approach to Jupiter at 36 cents on March 16, 2026. These planetary encounters, especially with Jupiter, could potentially offer gravitational assists or subtle deflections, though its high speed means these effects will be minimal. They also provide additional data points for tracking its trajectory and understanding its interaction with our solar system's gravitational landscape. Beyond its path, the physical makeup of 3IATLAS holds even deeper mysteries. What is this cosmic wanderer made of? What can its appearance tell us about its distant home? These questions drive astronomers to peer closer, revealing surprising details. Unlike the rocky ʻOumuamua, 3IATLAS is an active comet. This means it possesses a solid, icy nucleus that, when warmed by the Sun, releases gas and dust, forming a glowing cloud called a coma. This activity makes it much easier to observe and study than a dormant, rocky object. The coma acts like a giant, diffuse atmosphere, revealing the comet's inner secrets. The presence of a coma and tail is a clear indicator of its icy composition, similar to comets native to our own solar system. This suggests that the conditions in its home star system allowed for the formation of volatile rich bodies, much like our own Kuiper belt and Oort cloud. Determining the exact size of a comet's nucleus is challenging, as it's often obscured by the bright coma. However, initial estimates place 3I-ATLAS's nucleus diameter between 0.32 and 5.6 kilometers, with the most likely size being less than 1 kilometer. This makes it a moderately sized comet, comparable to many comets found within our own solar system. Understanding the nucleus size is crucial for estimating its total mass and how much material it might be shedding. Even a small nucleus can produce a spectacular coma and tail, especially when it's highly active. These estimates help us understand the scale of objects ejected from other star systems. Observations of 3I-ATLAS's coma have provided a fascinating glimpse into its chemical makeup. Scientists have detected the presence of water ice, carbon dioxide gas, and even cyanide gas. Most remarkably, atomic nickel vapor has also been identified. This diverse cocktail of elements and compounds offers direct evidence of the conditions in its birth environment. The presence of water and carbon dioxide is common in comets, but cyanide and nickel are particularly intriguing. Cyanide is a simple organic molecule, a building block for more complex chemistry. Nickel, a metal, suggests that the comet formed in a region where such elements were available, possibly hinting at the composition of its parent star's protoplanetary disk. One of the most visually striking features of 3I-ATLAS is its apparent backwards tail, which seems to point towards the Sun. This isn't a defiance of physics, but rather an optical illusion caused by larger dust grains. While the lighter gas and dust particles are pushed away from the Sun by solar radiation pressure, larger, heavier dust grains have more inertia. As the comet moves rapidly, these larger grains are essentially left behind in the comet's orbital path, creating a dust trail that appears to point back towards the Sun from our perspective. This phenomenon, known as an anti-tail or antitail, is a fascinating demonstration of the interplay between a comet's motion and the forces of the solar wind and radiation pressure. The true marvel of 3I-ATLAS lies not just in its presence, but in its origin. Where did it come from? What can it teach us about the vast, unexplored regions of our galaxy? Its journey holds profound implications for our understanding of the universe. The most profound fact about 3I-ATLAS is its interstellar origin. It did not form in our solar system. It was ejected from another star system entirely. This means it has traveled immense distances across the cold, dark expanse between stars, carrying with it the pristine material from its birth environment. It's a true galactic wanderer, a testament to the dynamic nature of star systems. This journey could have taken millions or even billions of years. It reminds us that our solar system is not an isolated island, but part of a much larger, interconnected galactic neighborhood where objects are constantly exchanged, albeit rarely observed. 3I-ATLAS has been approaching our solar system from the general direction of the constellation Sagittarius. This region of the sky is particularly significant because it's where the central bulge of the Milky Way galaxy is located. While this doesn't pinpoint its exact home star, it suggests a possible origin within the denser, more active regions of our galaxy. The direction of approach, combined with its velocity, helps astronomers trace its potential trajectory back into interstellar space. This information can be used to model possible ejection scenarios from other star systems, providing clues about the dynamics of planetary formation and stellar interactions in other parts of the galaxy. Initial studies of 3I-ATLAS suggest it could be incredibly ancient, potentially between 3 and 14 billion years old. To put that into perspective, our own solar system is approximately 4.6 billion years old. If these estimates are accurate, 3I-ATLAS could be a relic from the early universe, a time capsule from a much older star system. An object older than our solar system would be an extraordinary discovery, offering insights into the conditions and processes that existed in the very early stages of galactic evolution. It could contain primordial material that has remained largely unchanged for billions of years, providing a unique window into cosmic history. As the largest and brightest interstellar object discovered to date, 3IATLAS is an unparalleled scientific treasure. Its size and activity mean we can gather more detailed data on its composition and behavior than with its predecessors. This makes it a potential Rosetta Stone for understanding the formation and evolution of other star systems. By studying its chemical makeup, its physical properties, and its orbital dynamics, we can infer characteristics about the star system it originated from. This includes the types of materials available, the temperatures, and the processes that led to its ejection, painting a picture of worlds far beyond our reach. Interstellar objects like 3IATLAS are not just inert rocks. They are often rich in organic materials and dust. These components are the very building blocks of planets, and potentially, life itself. It's theorized that such objects could act as seeds for planet formation in other star systems, delivering crucial ingredients to nascent protoplanetary disks. Furthermore, these objects might have played a role in delivering water and organic molecules to early Earth, contributing to the conditions necessary for life to emerge. Studying their composition helps us understand the cosmic distribution of these vital ingredients and the potential for life elsewhere in the universe. Ultimately, studying interstellar objects like 3IATLAS helps us unravel the grand narrative of the universe. They provide direct evidence of the movement of matter across vast cosmic distances, the processes of planet formation in diverse environments, and the evolution of stars. Each piece of data contributes to a more complete understanding of our own origins and our place in the cosmos. These objects are tangible links to the broader galactic ecosystem, demonstrating that the universe is a dynamic, interconnected place. They challenge our assumptions, expand our horizons, and inspire us to ask bigger questions about the fundamental nature of reality and the potential for life beyond Earth. The arrival of 3IATLAS is more than just an astronomical curiosity. It's a profound moment for humanity. Its study touches upon some of the most fundamental questions we can ask about our existence and the universe around us. Studying 3IATLAS helps us understand the composition and formation of other star systems, expanding our knowledge of the universe far beyond our local neighborhood. It provides direct, tangible evidence of what other planetary nurseries might look like. This allows us to test and refine our theories about how stars and planets form across the galaxy. Each new piece of information about 3IATLAS is a puzzle piece in the grand cosmic tapestry, helping us to see the bigger picture. It's about moving from understanding our backyard to comprehending the entire galactic landscape. Interstellar objects may have played a crucial role in the delivery of organic molecules and water to early planets, potentially contributing to the development of life. Studying their composition can provide invaluable clues about the building blocks of life and how they are distributed throughout the galaxy. Could life's ingredients be universal? If these cosmic wanderers carry the very precursors to life, then their study becomes central to astrobiology. It helps us assess the likelihood of life arising on other worlds, connecting the vastness of space to the most intimate questions of our existence. These objects could act as seeds for planet formation, influencing the composition and structure of new worlds as they collide with and integrate into protoplanetary disks. They represent the raw material that gets recycled and reformed into new celestial bodies. This process is a fundamental aspect of how solar systems are built. By analyzing 3IATLAS, we gain insights into the raw materials available in other star-forming regions. This helps us understand why planets in different systems might have different compositions and how diverse planetary architectures arise. Researching 3IATLAS brings humanity closer to unraveling cosmic mysteries and understanding our place in the universe. It fuels our innate curiosity, pushing the boundaries of what we know and inspiring future generations of scientists and explorers. It's a tangible connection to the unknown. Every discovery like 3IATLAS reminds us that there is so much more to learn, fostering a sense of wonder and humility. It encourages us to keep looking up, to keep asking questions, and to keep striving for deeper understanding. The study of 3IATLAS requires advanced astronomical tools and techniques, from powerful ground-based telescopes to sophisticated orbital observatories. This pursuit drives innovation in fields like optics, data processing, and space engineering, leading to breakthroughs that benefit society in countless ways. The challenges posed by observing and analyzing such a fast-moving, distant object push our technological capabilities to their limits. The solutions we develop for these cosmic puzzles often have ripple effects, advancing technology for Earth-based applications as well. The story of 3IATLAS is still unfolding, and you can be a part of it. Follow the latest updates from NASA, ESA, and major observatories as they continue to study this incredible interstellar visitor. Share this knowledge with your friends and family, sparking conversations about our place in the universe. Most importantly, support scientific research and education, because every discovery, every new piece of knowledge, brings us closer to understanding the grand cosmic story we are all a part of. Let's keep looking up, keep learning, and keep exploring the wonders of our universe together.
Of a 2 trillion galaxy universe, but Hubble's view, for all its depth, had a limit. Its 2.4-meter mirror could not see the faint infrared light emitted by the most distant galaxies. Their ancient glow, stretched by the expansion of space itself, slipped beyond what Hubble could ever detect. James Webb, however, was built precisely for that. With a mirror 6.5 meters wide, more than 6 times Hubble's light-gathering power, and eyes tuned entirely to infrared wavelengths, Webb can pierce through cosmic dust and detect light from the earliest galaxies ever formed. If Hubble's vision was like peering through a keyhole, Webb's is like stepping back to see an entire cosmic mural. Imagine the Hubble ultra-deep field as a single sheet of paper. At the same depth, Webb's Cosmos Web would fill a mural 13 feet tall and 13 feet wide. Over 250 hours of observing time were devoted to this project, scanning a patch of sky 3 times the size of the full moon and stitching thousands of exposures into a seamless mosaic. The largest and deepest panoramic map of the universe ever made. Within that single image, astronomers identified nearly 780,000 galaxies, each a city of stars, some shining from just 400 million years after the Big Bang. The map is both wide enough to reveal the cosmic web of filaments, clusters and voids that shape the universe, and deep enough to capture its faintest, oldest light. It's not just a bigger picture. It's a new kind of cosmic atlas, one that challenges everything we thought we knew about the size, age, and complexity of the universe itself. For the first time in history, astronomers can now observe not just isolated galaxies, but the grand tapestry of the cosmos itself, the full sweep of structures stretching across billions of years, all within a single, continuous frame. Thanks to the James Webb Space Telescope's infrared vision and unprecedented reach, the universe has opened a new window on itself, revealing both its unimaginable scale and the hidden depths of its evolution within the vast Cosmos Web mosaic. In the nearby universe, this map captures a realm of fully mature galaxies, elegant spirals, smooth ellipticals, and chaotic mergers locked in gravitational dance. Astronomers can now trace how these systems weave together into colossal filaments and galaxy clusters, forming the immense scaffolding known as the cosmic web, the very backbone of the universe. Yet, among these countless shapes and collisions, one discovery stands apart, a system now known as the Infinity Galaxy. At a redshift of 1.14, this extraordinary object reveals itself as a glowing figure-8 silhouette. 2 disk galaxies colliding almost head-on. Each retains a compact red core, surrounded by luminous rings of stars and gas, their orbits twisted by the power of their cosmic encounter. The collision, which occurred around 50 million years ago, is more than a spectacle. It has exposed conditions never seen so clearly before. Between the 2 galactic centers lies a massive cloud of ionized hydrogen, glowing with the energy of something extraordinary. Deep observations from JWST and NASA's Chandra X-ray Observatory have uncovered the signature of a supermassive black hole. Not in either galaxy's core, but suspended in the void between them, embedded in the turbulent gas. Its motion perfectly matches the surrounding material to within 50 kilometers per second. This off-center black hole, about 1,000,000 times the mass of the Sun, is joined by two more, each galaxy's original core harboring its own active black hole, confirmed by their broad hydrogen emission lines. 3 active black holes, 2 anchored in their galaxies, 1 adrift between them. The evidence suggests the intergalactic one did not come from a merger or ejection, but formed directly in place, collapsing from dense, shocked gas funneled into the center of the collision. Captured mid-formation by Webb's infrared eyes, it offers a rare glimpse into how supermassive black holes might seed themselves in the chaos of galaxy assembly. The Infinity Galaxy is more than a curiosity. It's a revelation. Its figure-8 form, with a black hole growing in the emptiness between colliding worlds, hints that the universe's most powerful engines may sometimes ignite not at the hearts of galaxies, but in the turbulent regions where galaxies themselves collide. It's a discovery only possible through Webb's panoramic view, a cosmic event so complex and fleeting that it would have remained invisible without the vast, deep field of the Cosmos Webb survey. From here, the journey continues deeper into the mosaic, back to an era astronomers call cosmic noon, roughly 10 billion years ago, when the universe was at its most prolific in forging new stars. The galaxies seen in this epoch are astonishing, vibrant, dynamic, and yet surprisingly mature. Webb's infrared vision reveals galaxies that appear far too organized, far too calm for such an early time in history. Even more puzzling, some of these galaxies, the so-called quenched systems, have already stopped forming stars entirely, despite existing in a period when the cosmos should have been ablaze with stellar birth. These dormant giants, with masses rivaling today's largest ellipticals, sit quietly amid a universe that theory once predicted would be wild and chaotic. But Webb's discoveries keep defying expectation. Among them are spiral galaxies, with beautifully defined arms and even central bars, signatures of stability and maturity, appearing just 2 to 3 billion years after the Big Bang. In cosmic terms, that's impossibly early. Yet here they are, massive, symmetrical, and serene, their spiral arms winding gracefully around dense cores. The James Webb Space Telescope has revealed not only a deeper universe, but a more advanced one, a cosmos that grew up faster, structured itself earlier, and hides far more complexity than anyone ever imagined. The data now reveals something astonishing. Disks capable of supporting spiral arms and stable structures were far more common, far earlier than anyone ever thought possible. This early order isn't just a matter of beauty. It's a fundamental shift in cosmic history. The existence of stable, well-formed disks and quenched giant galaxies during cosmic noon means that the forces shaping galaxies and shutting down star formation must have acted with incredible speed. The timeline of complexity in the universe is shrinking. Each of these galaxies becomes a vital clue, a piece of evidence that forces astronomers to rethink how fast the cosmos can evolve, how quickly it can transform from chaos into structure, from turbulence into order. The universe's growth, once thought to be a slow unfolding, now appears as an explosive acceleration. Webb's map isn't just more detailed. It's rewriting the rules of how galaxies grow up. At the very edge of what the James Webb Space Telescope can see, we now find the farthest confirmed galaxies ever detected. The record belongs to JADA's GSS Z14, whose light began its journey just 290 million years after the Big Bang. Close behind, Mam Samin Twin. Salin The-14 shines from only 280 million years after the beginning of time itself. Both have been spectroscopically confirmed, their distances precisely measured by sharp Lyman breaks captured in Webb's NIR spec data. But the revelations go even deeper. Using the Atacama Large Millimeter Array, astronomers have detected oxygen within JADA's GSS-14, a stunning discovery that means heavy elements already existed less than 300 million years after the Big Bang. That's evidence that at least one full generation of stars had already lived, burned, and died enriching these young galaxies with metals forged in their cores. Each of these systems shines with the light of hundreds of millions of suns, compressed into compact, furious starbursts. Their existence, and their chemical fingerprints, suggest that galaxy formation and stellar evolution began at a breathtaking pace. Within just the first 300 million years, the universe was already busy building complexity, forming stars, and creating elements that would one day make planets and life possible. The flood of discoveries pouring in from Webb's vast new map is forcing astronomers to rethink the entire story of cosmic dawn. We now know that galaxies and black holes emerged earlier and grew faster than any previous model allowed. Even these distant record holders, JADES GGS Z14 and MAMZ Z14, contain heavy elements, proof that cycles of star birth, death, and enrichment began almost immediately after the universe was born. What once seemed like a slow, billion-year climb toward complexity now looks like a cosmic sprint. The old narrative, a gradual evolution from simplicity to structure, has been replaced by one of rapid transformation. The processes of reionization, the growth of massive halos, and the birth of supermassive black holes all appear to have accelerated beyond expectation. The universe's earliest chapters are being rewritten in real time, and each new discovery from Webb raises deeper questions about how it all began. In just 250 hours, the James Webb Space Telescope's Cosmos Webb survey mapped nearly 780,000 galaxies, almost 80 times more than Hubble's ultra-deep field revealed in 2004. This sweeping infrared panorama captures galaxies and cosmic structures stretching back 13.5 billion years, including record breakers like JADES GS Z14 and MAMZ Z14, both seen less than 300 million years after the Big Bang. Webb's data show that mature spiral galaxies, colossal mergers, and heavy elements all appeared long before theory predicted. Yet the mysteries remain. How did galaxies and black holes grow so fast? What hidden roles did dark matter, turbulence, and feedback processes play in shaping them? Every observation brings us closer to understanding, and yet also reminds us how much we still don't know. Because even after mapping nearly 1 million galaxies, this survey covers only a tiny patch of sky, a fraction of what's out there. It's a humbling reminder that the universe is vastly larger, older, and more intricate than we ever imagined, and that Webb has only just begun to show us what lies beyond.